Hello everyone, I am Harish Rajan, a junior with Murrow Catholic High School, doing this small video for Bay Area SfN Youth, a society for neuroscience run primarily by the motivated high schoolers who are passionate about neuroscience and looking to expand their knowledge in this field. It is well represented by most South and East Bay public and private high schools. We have regular meetups almost every month during the school year. You can find more information about us at bayareasfnyouth.org. Now, let's get into this presentation. So, what is deep learning? Neural networks basically mimic the human brain and enable us to build a model learning from observational data. It can be used in image recognition, speech recognition, and anomaly detection, and many. Let us do a quick comparison between biological neural networks and artificial neural networks. I've written a small article for Bay Area SfN Newsletter 3. The image below represents a perceptron, which is very similar to the neuron in the human brain. We are passionate about neuroscience, and we know how biological neural networks operate. A large number of tiny cells, called neurons, form a network through synapses. The neurons get the inputs from other neurons through dendrites. They produce the output and pass the signal to the other neurons through axons. Our brain has a complex feedback mechanism built naturally with inhibitory and excitatory connections between the neurons, helping in adjusting the weights of the connection strength. When we go to artificial neural networks, all these understandings will help us to draw parallels. Now, let's go to artificial neural networks. With the advent of GPUs by NVIDIA and now TPUs by Google for processing huge volumes of data and development and release of many popular frameworks such as TensorFlow, PyTorch, Caffe, and Keras, deep learning is in the early stages of finding its adoption in every field. In fact, deep learning is revolutionizing the medicine and radiology scans and even in drug discovery. What are convolutional neural networks? CNN is a type of neural network used in image recognition and processing. CNN has a network of interconnected neurons arranged very similar to the human brain and our frontal lobe, where visual stimuli is processed. By the way, the latest advancement in deep learning, aided with computer vision developments, helped popularize an algorithm called convolutional neural networks. The origins of CNN, as shortly called, can be traced back to the 1980s. CNN is being used in medical imaging, like for processing fMRI images of the brain, and helps in diagnosis of cognitive impairment. What we will be doing in this session is to build a convolutional neural network, primarily for image detection. So let's quickly talk about the MNIST dataset. Take a look here. There are over 60,000 training images and 10,000 testing images of handwritten digits from 0 to 9. And these black and white images are downstamped to 28 and 28 pixels. Actually, 20 by 20. But for this session, let's just say 28 by 28 pixels, while retaining the aspect ratio. We'll be building an application to detect the digits 0 to 9 in these images. So we're going to switch to my browser, and I'll show you my notebook. So for this video, I'll be using Google Collaboratory Notebook to write the code, and Keras and TensorFlow to build my code, which in fact uses the Python language. So Keras is an open source neural network library and is capable of running on top of TensorFlow. TensorFlow is used to build the neural network applications. Some familiarity with Python language will be helpful to follow the steps. This notebook will be connecting to Google's cloud GPU to run our code and process the data. Give me a minute and I'll connect to the new instance. Yep, we're connected. Let's walk through the code. You can see in the first step that there are a bunch of imports. We import from NumPy and matplotlib libraries as well. NumPy is a Python library that supports large, multi-dimensional arrays and matrices. Remember that all the images we see are represented as two-dimensional arrays, and they contain pixel values. Matplotlib is a plotting library for the Python programming language. Let's run the step. TensorFlow version 2.2. Good. So the next step has helper functions. So this has nothing to do with convolutional neural networks, but it helps in plotting and for other visualizations. Let us not worry about this for now. Let's just execute the step. The next step is to show the hardware we're running on. Thanks to Google, we are running on the free version of their GPU hardware. Yes, it has one accelerator. This is more than fine for a simple application. You can upgrade to Colab Pro if you want to use more powerful hardware. So let's understand a little bit about the training and validation dataset. The training data will be used to fit the model. The model we are building sees and learns from this data. It means the weights and biases are calculated based on this training data. Validation dataset is used to find an unbiased evaluation of a model. And in this case, the model may be fit perfectly for training data and may not fit for other data. So it really depends. Hence, you check if the model has overfit to the training dataset using the validation dataset. So now let's jump back to the slides. Since each image has 28 by 28 pixels, there's a lot of 784 pixels in the image. Now, let's translate that to the neural network input layer. We have a total of 784 neurons for each pixel in the image. Now, let's look at the output layer. We have 10 neurons, and it maps to 1 neuron for each digit. In between these two input and output layers, we can have many hidden layers. How many neurons are in each hidden layer depends, and it varies. Each hidden layer can have a variable number of neurons. And what I mean by that is that the first hidden layer can have 64 neurons and the second one can have 32 neurons. Now, let's get a high level idea of how these layers look. Just take a look at the input layer on the left, and it takes the 28 by 28 images as input. And the last output layer does a classification of the digits. It tells you what is the most likely number, whether it's 7 or 9 or 2 or 0. I got this image from one of the Medium articles written by Summit, and I've added to the last slide with the links. I will highly encourage you to go and read those links for better understanding. In between, there are two Con2D layers that can process the images and one dense layer. And we will cover that when we talk through our code. But this visualization will have a broad overview. Now let's go back to the code. We'll be looking at the parameters now. All the images are in Google Cloud Storage buckets, and the images are loaded from these paths. MNIST public is the name of the bucket, and in that we have train and validation images in different paths. This neural network is trained using the stochastic gradient descent algorithm. And this algorithm uses training dataset and estimates the error gradient for the state of the model and tries to optimize how adjusting the weights of the model using a technique which is known as backpropagation. Now, how much weights should be updated while training the model is determined by the learning rate hyperparameter. If the step size is too small, then it means that the learning rate is small and that the training the model will take too long, suggesting that the training error is still high and may take a long time to improve. If the learning rate is high, on the other hand, the gradient descent can jump and may not optimize well, resulting in a high training error. This is the most important hyperparameter being discussed. Now, there are a number of learning rate schedules, including time-based decay, for example, or step decay, and exponential decay. And here, as you see, we're using exponential decay. You can also use learning rate scheduler in Keras to create your own custom learning rate schedule. Now let's go to the Medium article now. Take a look at the image. This is the fundamentals of how convolution works. So we're seeing a 5x5 image here, and we've numbered the pixels to make it easier to see how the 3x3 drop moves to calculate the elements of the filter. The result of applying the convolution operation returns the filter that we have represented on the right. Each element of this filter is labeled with a digit that associates it with the content of the sliding window, which is what the value is calculated, shown here. And a similar effect can be observed in the convolution neural network. So now going back to the code. There are again simple steps to load all the training and validation images dataset. There's nothing fancy here. So we can take a look at the images here in the step. Now we're at the heart of the application. So let's build a model. So the word sequential means linear stacks of layers. We're adding lists of layers to the model. The first layer can receive an input shape argument. Afterward, we can do automatic shape inference. So we use 2D convolution layer, as this is spatial convolution over images. And the convolutional layer is used to detect visual features in images like edges, colors, lines, and so on. Filter defines the dimensionality of the outer space. And the number of output filters in the convolution is being defined by filter. Now, layers really close to the input have fewer convolutional filters, while layers closer to the output predictions will have way more filters. So kernel size. Kernel size is the tuple of two integers, seen here, bolded, specifying the height and width of the 2D convolutional window. It is recommended to be an odd integer. What are strides? Well, strides are usually a tuple of two integers, specifying the strides of the convolution along the height and the width. So the padding parameter to the Keras conv 2D class can take one of two values. It can be valid, or it can just be the same. So with the valid parameter, the input volume is not zero padded, and the spatial dimensions are allowed to reduce through the natural application of convolution. So what does a dropout do? It ignores some neurons randomly in the hidden layers during the training phase. So this is basically done to prevent overfitting. And there's another variable, there's another hyperparameter we use, which is called regularization. And it essentially does the same thing. It prevents overfitting. So let's compile. And let's also print the model summary. So let's go back to the slide on activation functions. So the perceptron, which we saw earlier, which is very similar to the neuron, is essentially a single layer neural network that takes all the input values and computes the weighted sum using the weights and bias and applies a function called the activation function. So what does the activation function do? Well, the activation function finally gives a range between 0 to 1 or between -1 and 1, depending on which activation function you see. So we have a simple linear activation where no transformation is applied. It can't learn complex mapping functions. But nonlinear activation functions, on the other hand, allow learning more complex structures in the data. Some of the most popular activation functions are the rectified linear unit, sometimes referred as a ReLU, and the sigmoid and hyperbolic tangent functions, all shown here. So sigmoid provides a smooth gradient, and the values range between 0 and 1. And ReLU, as shown here, will give 1 for all positive values and 0 for all negative values, which is clearly shown, the graph on the left side. And it accelerates the convergence of the stochastic gradient descent, which we discussed earlier, compared to the other activation functions like the sigmoid. So now let's go back to the code again. Here in our example, we used sigmoid and ReLU. So we use softmax as well. And we will have a session exclusive to activation functions, as they're the most important piece of this deep learning puzzle. The final classification uses the softmax classification technique. Max pooling is a simple mathematical operation to find the maximum. Max pooling returns the maximum value from the portion of the image covered by the kernel. It discards the noisy activations and can perform denoising and dimensionality reduction. So there are a lot more hyperparameters that we can discuss, and we're just getting started here. In our future sessions, we will cover kernel regularizer, bias regularizer, and other ones like activity regularizer. And also, in the future lesson, we'll be talking about batch normalization and hyperparameters tuning. Now let's see the summary. There's a lot of good information about the parameters of each layer and the shape of the output tensors of each layer. So the model summary tells us more about each layer. So right now we just saw how to build the layers, and this summary gives us the output shape and C's after the flattening. So let's start with an input image of the 28 by 28, and we resulted in the 14 by 14 pixeled image after the first convolutional layer. In the second convolutional layer, we went 4 by 4, and since we gave 2 by 2 for the max pooling values, it calculated the maximum value in each patch of the feature map. Hence, the 14 by 14 pixels became 7 by 7, and similarly the 4 by 4 became the 2 by 2. So there are only a few steps more. In the next step, we will be fitting and evaluating the model. To build a model, we will need to pass epoch. Epoch is a measure of how many times all of the training data is used to update the weights. It is applicable to iterative algorithms. And here, in this example, we defined 10 algorithms, 10 epochs. And we can even define 5 epochs, but the accuracy won't be that high as 10. With every epoch, the accuracy improves until a certain point. Now, let's run. If you look at the first epoch, the accuracy is 92.44, and it increases to 96.83, then 97.86 in third epoch, and so on. So we can see that as the epochs increase, the accuracy is also increasing, and the 10th epoch, we ended up with an accuracy of 99.35, which is really high. So also, you can also notice that learning rate, which is abbreviated LR. And it also is getting adjusted, and it's lowering. We can see that here. So recall that we use exponential decay learning schedule. Finally, our model can predict the digits fairly accurately, like almost 98.8% accurate. So this is against the training data set, but we still haven't exposed the validation data set. Now, there are plenty of hyperparameters that we can tune to improve the accuracy further. But this is our first session, and we just want to get started. Now we built the model. Let's see how the model performs against the validation dataset. We are showing the validation data to the model, and we're going to see how the model predicts. Let's run it. And as you see here, it looks like 168 samples out of the 10,000 had bad predictions, which means that we had really high accuracy. Yeah, so that's 9,832. So in percentage, it's 98.32. So 98.32% accurate, which is really good. So let me show you how the websites that I referenced to come up with this presentation. So thank you so much for watching, and we'll have more sessions to advance this to the next steps. Again, don't forget to subscribe to Bay Area SfN Youth's YouTube channel. And if you think the video is helpful, you can like it. Thank you.